Cooperative Adaptive Cruise Control, or C-ACC, is a connected vehicle advanced driver assistance system designed to synchronize and coordinate traffic. By exchanging critical real-time vehicle data such as speed, acceleration, and position, it can automatically calculate and adjust the vehicle's speed to maintain a safe distance from others. This leads to optimal traffic flow and efficient roadway capacity usage. At least that's the theory, provided the data is trustworthy. But what if the ECU transmitting the data gets hacked? The focus of the second Connect use case is to ensure the safe operation of C-ACC by assessing trustworthiness at runtime and responding to changes with appropriate actions. Use case setup. For this use case setup, Sumo is used, a traffic simulator where 3 vehicles are defined driving in a circle. The first and last vehicles are controlled by Sumo, while the red vehicle in the middle, the subjective ego vehicle, is managed by 2 Intel-based electronic control units, the Vehicle Computer 1 or VC1 and the Vehicle Computer 2 or VC2. Only one computer actively runs the C-ACC main function and connects to the simulation platform via Kafka. However, both computers are capable of performing this function. If the active computer becomes compromised and its trustworthiness level drops, the backup computer can take over. These trustworthiness changes are detected by the Trust Assessment Framework, also known as TAF, which evaluates trust evidence from the Attestation Integrity Verification or AIV module. This framework calculates the actual level of trustworthiness based on collected trust evidence from both vehicle computers. When VC1's actual level of trustworthiness no longer meets the required level, the TAF decides to respond to this by initiating the migration process. For this, the TAF confirms that VC2's actual level of trustworthiness meets or exceeds the required level before starting the C-ACC instance on Vehicle Computer 2. Once the transition is complete, VC2's status turns green, indicating its new active status, while VC1 is disconnected and its status turns red. This marks the end of the migration process. Proof of concept implementation. Now we show the proof of concept implementation of this system. Testing setup looks as follows. The simulation application Sumo with its 3 vehicles can be seen in the top left. While the vehicles controlled by Sumo are marked in yellow, the red one, the subjective ego vehicle, is controlled by 2 Intel-based ECUs, the Vehicle Computer 1 or VC1 and the Vehicle Computer 2 or VC2, seen on the bottom left side. VC1 status turned green, indicating the active Cooperative Adaptive Cruise Control application. On the right side, we see the actual trustworthiness assessment or ATL of our vehicle computer's integrities in the form of dots in a triangle. The full triangle shows the space of all possible trustworthiness assessments according to subjective logic, while the blue area inside is the RTL, which means the space where the ATL fulfills our C-ACC's requirements. If a dot is inside the blue area, then the vehicle computer's integrity is trustworthy. If it is outside, then C-ACC will start the migration process to switch to a more trustworthy vehicle computer. The trustworthiness assessment is based on evidence provided by the trust sources shown below the triangle. Each vehicle computer implements a set of mechanisms to monitor different technical aspects indicating the status of the computer's integrity. Here we see that all mechanisms show a green status, meaning no anomalies are detected. When our VC1 source access control turns red, we see how the updated ATL dot in the triangle moves outside of the allowed blue area. This triggers our migration process. Now we see what happens when the migration is invoked. First, the C-ACC application stops running on VC1 and starts on VC2. Second, the status indicators switch colors. VC1 turns red, which means inactive. VC2 turns green, which means active. Finally, VC2 successfully takes control of the ego vehicle's speed. With that, we conclude the explanation of this use case. Thank you. If you want to know more about the EU-funded Connect project, head over to horizon-connect.eu.